Our second week of physics, and welcome to all the new people. I got several emails that a handful of people wanted to join this class, so if you're here, welcome, welcome. Those of you that haven't, if you're new and you've added this course, after you've gone to Canvas and read the instructions where you can see the syllabus and head over to WebAssign and learn everything, if you can't get into WebAssign, I need to know. I guess one student's having an issue, even though I gave him access, so I haven't figured that out yet. But email me and let me know those things if you're having issues getting into the class. You guys have any questions about logistics or the topics we've covered thus far? Anything that you lost sleep over the long weekend? Well, it's okay if you don't. It means you're all happy and comfortable. If you think of one, raise your hand. Today we continue with Chapter 3. We didn't officially start it, but we've discussed many of the things in it already. Chapter 1 was about science. Chapter 2 was Newton's first law of motion, inertia, that resistance to wanting to change. Now we're Chapter 3 will kind of take a break from Newton's laws to make sure we understand the terms of motion and motion itself, like velocity and speed, acceleration, force, gravity, free fall, those type of things. Then the next two chapters can do Newton's second law and Newton's third law. That's our game plan. I remind you too that it's all on the schedule on WebAssign, if you want to know. You guys excited? You look kind of blasé. Oh, I'm glad you're back. Thanks for coming. Well, today I said it would be our where we could start checking out clickers, where you should all have them and be registered by now. So we'll try it out. You'll see what it's like, and I can see who hasn't done things. So once I connect and project, you can see what I'm doing here. Meanwhile, let me close a few things. Hide that. 12 and 18. Okay. Okay, so I get this little receiver that picks up all your transmissions from your mobile devices, and your clickers.
Mine doesn't work.
I haven't done anything yet, so it can't work.
It's never going to work.
Be patient. All right. So one thing you can see here, this will be a typical look of how things are going to be. I'll ask a question or show a slide like this. All right, in the upper right-hand corner is where I'll hit play, and I'll open it up so you can start responding. You can't right now. So those of you that have clickers, it's channel 41. So if you need to set yours to channel 41 so that it'll work here. That's typically the default, but you follow your menu and hit channel. Mine has a button that says channel. Yes?
With the ResponseWare,
I'm getting to it. First, clickers first. Those that have clicker, you need to be on channel 41. Or it won't work yet. But it doesn't work yet because I haven't opened up the polling. Yes? I can't hear you. That's my intent, yes, because I warned you to have it by now. But I'll admit, if over half the class or something don't, then I'll be lenient. I'm going to see how it is first. You forgot to bring it this time? In the back of my mind, this will probably bomb and fall through, and I won't take points. So you're probably okay. I'll be honest, that's the way I'm leaning. Since it's the first time we've done it. But most of you that were here from the beginning of our class have had time and should have. All right, that's clickers. ResponseWare, I get to do this. Each time I come, hit ResponseWare, I log in, and boom, we get a session ID number. It's in the bottom right there next to the channel, bottom right of the screen. So the clickers use channel 41. Those with ResponseWare enter that session ID. I've learned that if you have from Google Play or iTunes, you can download apps for your mobile devices. But if you have Windows or you're using a laptop or some other platform, then they have provided that link I gave you in the syllabus. You click on it, and you just enter the session ID, and you do it that way. So for example, from your phone, your browser, you would pull up that link, just enter the session ID number, and you should be able to do it that way. To remind you for future reference, let me pull up the syllabus. Okay, in there. So here's the beginning. Scroll down. Second page. Class participation, where it talks about the audience response system. Getting it, registering. And there it is. To use your clicker in class, right here. Make sure your device is on the same channel. We covered that. To use your mobile device, you log into ResponseWare, either through your app that you've downloaded for free after you've got purchased a license, or through this website. So this link right here takes you to a web page that should pop up here in a second and looks like go web. Come on. You can do it. I know you can. Something like that. So you would enter this session ID number in the lower right-hand corner that I've provided for you this time, right in there, join session, and it should allow you to participate. A what? Have you registered your mobile device? And did you receive an access code? Now they send you a device ID. So if you did all that, who else is using ResponseWare? Let's see your hand. How many? Hi, I can't. Okay. Now raise your hands if it worked. Raise your hand if it didn't work. 3. Okay. Are you guys logging in like this, or do you have an app? Yeah, you had your hand up. I'm asking you a question. But the app's not working yet? Oh, you had your hand up when I said it didn't work. Okay. How about you? What's going on with yours?
Well, I'm trying to get into the session right now, but I forgot what email I used, but it's working.
Oh, okay. But yeah, you had to choose an email.
Yeah.
Did it ask you for a password?
Yeah, I forgot both of them.
So, and it would have asked you that as well. That's how you would sign in.
I put the session ID, and when I do it.
Yeah, so enter that and hit join, and then let's see what happens. Isn't this fun? Hit join session.
She may not have created a profile yet.
I did.
Well, then that's what you chose when you made your profile. You had to give them your email and choose a password when you signed up. That's what it's requiring. So if you can't remember this time, we'll try again Wednesday. This is Wednesday. Friday. All right, let's ask a question for those. The large majority's working here. And see how it works here. So it'd be like this. I hit play, and now it's open. Time's going. You ought to be able to respond. So like here, choose A, B, C, or D. if you try it out. Pick one. Change your mind. Pick a different one. On your clicker or ResponseWare, you ought to see a smiley face or a check giving you some type of confirmation that, yeah, it worked. It took. And it's still open. I usually get a feel. I can see the number of responses. 33 people have responded thus far. And so when I get a feel how many people are here, I'll start counting down to give you a warning. We're going to close the question.
So I'm not getting a smiley face or anything. So this is the answer I want. Push that, and nothing's happening. Like channel 41 right there.
Sorry, I just can't see it that well. All right, let's see. Yours isn't doing diddly.
Yeah.
Let's do inner. Channel
That
changed.
changes it.
Okay, maybe it hadn't finished the channel thing. Now
So
let's
you
do
gotta find
A.
it. So now it's looking for channels, actually.
Where's it looking? We want it to be 41. Okay. Channel changed. Now it's definitely 41. Let's go for it. A.
Oh, okay.
Now put whatever you really think it is. And how's some people's ResponseWare working? We've gotten 35 people to respond. There's more than 35 of you, so several of you, I hope it's mostly because you haven't gotten one yet or figured it out or the new people didn't know yet. You just did it? That's all spelled out in the syllabus with the links and everything to do it. With your clicker, there's a device ID on the back. For ResponseWare, after you purchase a license, following the instructions on the syllabus, they'll send you in your email a device ID number. Up to that point, this should still be working. But you do need to take your device ID number and register it in Canvas, again, per instructions. It says that there's a module in there for clicker registration tool. That way you get points. See, I'll get to look after class that I have all of these responses associated with your device ID. But until you register your device ID, I don't know it's you. So I got your response, whatever it was today. And once you register, or if you have, now I can give you points. So that's why you have to register. And I'll look and see who hasn't after today and say, oh, you did it wrong, or you haven't done it yet. Make sense? We'll have fun with this. You know, once we get past this, it's fun the rest of the semester, I promise. Okay, obviously this has been open a long time. So, you know, I would count down 10, 9, 8, 1, stop. There's your responses. 50. Oh, the majority of you think it's A, but a lot of you think it's D. You know, that tells us a lot. You know how other people are thinking, and I know how you are thinking. So we can nip things in the bud right now. So I don't even remember the question. I was just going over logistics here. Which of these is not a vector? You guys, most of you think it's speed. The rest of you think all of them are vectors, meaning speed's a vector as well. Well, the majority is correct. Speed is not a vector. It's a magnitude only. It's just a value. It's like 55 miles an hour. But there's no direction associated with it. We say speed is a scalar. A scalar. And again, this is all in your book. But the others have a direction associated with that magnitude, so they're vectors. Questions? So if I was you, and see, you don't have to be embarrassed this way, and you answered D, does it make sense now? It's something that most people are getting, and obviously I've chose this question, so I think it's important, and it kind of tips you off that, oh, okay, make a note. I got it now, or I need to go over that more so it's more solid understanding before test time, right? Let's try another one. Okay, I learned I didn't want to hit escape. Darn it. I just wanted to escape PowerPoint, not turning point. So, it's clicker time. I choose polling. And I want to See, I got to remember too. I'm rusty. Okay, so new question. Polling's open. What do you think? The space probe in remote outer space continues moving. Which of these best answers the rest of that statement? These questions are off of Chapter 2, Inertia. In theory, we just finished, so I'll usually ask these questions after we've gone over it a little, or as teasers as we continue the next lecture. So they should be relevant. And based on having 35 responses last time, there's only 3 of you slacking, so 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. No new people. Stop. And by far, most of you think C, which is even though no force acts on it. That is correct. I'll give you the answer. Correct answer is C. Why? That's inertia. Things in motion want to stay in motion unless or until something acts on it. So if nothing acts on it, it'll just keep doing it the way it wants to.
Now it's telling me that please wait for your presenter to open.
It's open. Oh, right now it's closed. Okay. So maybe the next question will work. I got another one. I wanted to comment though, one of the homeworks, forgot how it worded it. Say you're at rest, and then some force acts on you to get you moving, and you start moving. If you eventually stopped moving, does that violate Newton's first law? So an object's at rest, some force causes it to move. It's moving, but it eventually slows down and stops. Is Newton's first law violated? No. Now, most of you answered no. The reasoning. Well, it just said, though, things in motion want to stay in motion. So 2 things are happening here, and I want to clarify them. Things at rest want to stay at rest. And that's what happened until you exerted a force on it, and that changed its motion. So it sped up. Okay, but now that's gone. Now we're moving. We're happy moving. And things in motion want to stay in motion. So why did it stop? Good. We don't know what force, but you know enough now to know for sure that some other force must be acting on it to slow it down. Otherwise, it would keep going forever. So we didn't violate Newton's first law. We started imploring Newton's second law. That force causes an acceleration, a change in motion. Okay, let's try another one. All right, I'll open polling now. Yay! It's always good. So you got 2 ropes hanging down, and they're both supporting the same object that is 10 newtons. So what's the tension in each rope? The object weighs 10 newtons. You got 2 ropes holding it up. What's the tension, which is force, in one of the ropes? Each rope. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hey. Oh, we gained somebody. Which is yours? All right. 83% think it's B. You're right. Very good. That's this equilibrium thing. If it's supporting it, it's in equilibrium. which tells us the net force is 0. All the forces must be balanced. If the object is 10 newtons down, that's its weight, right? Then there must be 10 newtons up, correct? But there's two things supporting it up, each rope, so they split. This one will take 5 and this one will take 5. Does that make sense?
Yep.
All right. I'm sorry, I couldn't make out what you said. Oh, the cartoons help? Yeah, see pictures. So there we go. We'll call that good. We would do things like that often. So most of the time, my clicker questions will be like that. Occasionally with demonstrations, I'll ask you questions on the fly. We don't need the screen. I can just say, A, B, or C, to the left, to the right, or in the middle. And we can vote on the fly anytime we want. Sometimes I just ask you outright because it's quicker. Yeah? So the clicker, you get participation points for sure. So you come and answer all the questions, you get full points. You saw in the syllabus the clicker is worth 10% of your overall grade. Because I want to encourage you guys to participate, to be here and be engaged. Remember, that's one reason I chose to use clickers, because not everybody responds. And a lot of people, be honest, when I ask questions, you want to sit there and go, I don't know. I hope somebody answers. I know he's going to explain it. I don't know. But I want you to commit. You'll learn more if you choose an answer, even if it's wrong. Once you learn the correct answer, you'll retain it longer. You'll understand it a little better than if you just sit there like a bump on a log. So that's the main thing. But yes, I'm going to give you even less points. So it's like it's going to be like a point for every question. If you answered all of them, you got all points today. If you got them right, you'll get like another half a point. If you get it wrong, you'll miss out on that. And that's to encourage you not to just guess. Oh, who cares? I'm here. D. I don't care. But also, if you study and you've looked at this stuff ahead of time, you've given this some thought outside a lecture, you'll get credit for that. And I've mentioned that to you too. If you have read this or thought about this or even just skimmed over the chapter, looked at your notes again, at any point in time other than when we're together, when we go over it again and you see homework and you review the video or whatever, then it'll stick even more. A lot of people, it takes, 7 times before it sinks in? So that's to encourage that also. So yes, you'll get full points if you participate, and you'll get a few less points if you actually get it right. Groovy? Ready to discuss some more physics then? Okay. So, Chapter 3, linear motion. Some more on that. Make sure we got some definitions and units. We're all on the same wavelength as we go forward, adding more. First of all, linear, fancy term for straight, in a straight line. Linear just means in a straight line. And again, all of this is in your book. Definitions, so if you forget. But we had speed. And we just reviewed that with the lecture, or the clicker question. But there's a relationship for it. It's distance over time. And somebody knew that because you told me a lecture or so ago. Most people know this. If you're going 55 miles an hour, you go 55 miles in 1 hour. It's a distance over time. That's how you find it. That's the relationship. It's telling you how quickly you change your position. See, this covers a certain distance. It's a displacement. And if you do that in less time, then you were going faster. If you do it in longer time, you're going slower. This makes sense to most people. Another way to think of speed is then a change in position. And that takes a certain amount of time. Remember, this is our Greek letter delta, that means change in a certain amount of time. So there's two kinds we often refer to: instantaneous, and average. Instantaneous speed is just that. It's a speed at any given moment. That's not spelled still right, is it? Instantaneous. There we go. That's at a precise moment. On average, you can say you're going whatever, a different speed. So, if you're tooling down the road at 55 miles an hour, that at any given instant, like right now, we could say your instantaneous speed's 55 miles an hour. But you speed up, you slow down, you don't have cruise control, you kind of oscillate around 55, right? So on average throughout the trip, we'd say you went 55 miles an hour. But at any given instant, you could have been going 60 miles an hour or 50 miles an hour. That make sense? So average is over the whole trip. So it's like it's the same formula, equation to guide our thinking. It's a distance covered in a certain amount of time. For average, you're just kind of looking at the whole trip. Where in an instant, you're looking at a really, 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 really small distance. So we can say, oh, right here, at that instant, when I covered that millimeter of road, I was going this fast. With me? All right. So the average is just the total distance, if you want to think of it that way, divided by time, where the instantaneous is any small little increment of it. How is velocity different? That's it. It's the same as its speed with direction. It's a vector. So everything we just said still applies. You can think of it, velocity is distance over time. It just includes the direction you're heading. You can have instantaneous velocity and average velocity. When I was a kid, I remember distance equals rate times time. Anybody else learn that? Distance equals rate times time. That's still ingrained in my head. That's the same thing. The rate is what you're changing, your velocity. And that's time. So that's just velocity times time. Here's some algebra. Do you see that these are the exact same equation? Just rearranged? Please tell me now if you can't see this. I'll work it out because I expect this much algebra in this class, and so I might as well help you right now. Don't be embarrassed. Okay. So in order to get v by itself, we need to get rid of this t. So to get rid of that t, I could divide by the t and it would go away, wouldn't it? But if I did that on that side, you have to keep things equal and do it on this side. Divide by t. Now do you see it's just velocity equals distance divided by time. You'll do that with multiplying, adding, subtracting, and it's just a way to rearrange the equation. Because sometimes the question will ask you for velocity and you have these two. But sometimes it'll ask for the distance covered and you'll only have these two. So it's helpful to rearrange the equations. Oh, I don't think I mentioned. Our TA chose office hours, which I posted as an announcement in WebAssign. So her name, office location, and hours are posted. And it was an afterthought, so I can't remember. It was like Wednesday afternoons, I think she picked. So for those of you that works for, awesome. You're welcome to contact her and see if some other time works too, and me as well. But that's a set time for you guys, if you want help from Jing Ma. So, acceleration. That's a change of what? For the rest of you, you just weren't sure? Yeah, we've talked about this. This causes a change in motion. The motion we're dealing with is our velocities. So yeah, acceleration is just a change in velocity over time. I know some student already asked me, because they've had calculus, if you've had derivatives, if you don't know what I'm talking about, ignore me, but in calculus they do derivatives, and that's just a change in something. So here's the connection. You have a certain position. It's actually kind of like you're at point X on a timeline. If you change your position, you've covered a certain distance, right? From X final to X, or X initial to X final. To get there, you had to move. A velocity is a change in position. Change your position, you needed a velocity to do that. If you change your velocity, it's called an acceleration. That was lame. There. So a change in position is velocity. A change in velocity is acceleration. And we've already learned, in order to have an acceleration, you need a net force. So if there's a net force, you'll have an acceleration, which means you're changing your velocity. And you're speeding up or slowing down. Or changing direction, because it's a vector, and that would change it. So again, another way, might help some of you. You can think of it as that too. It's the same thing rearranged. If you accelerate at a certain rate for a given amount of time, it'll tell you your change in velocity, how much faster you're going, or slower. And we have one acceleration you guys can't really get away from. The acceleration due to gravity. We usually call that g. It's an acceleration, though. So, if we want to know how fast we're going, see a change in velocity, and you accelerate downward because you're falling at that rate for a certain amount of time, you'll know how fast you're going when you hit the ground, right? Or how much faster. Or how much slower you are on your way up. Let me go ahead and say G, as most of you knew and the book explained, is technically 9.8 meters per second squared. Half of you probably already knew that. For this course, I have to admit I like writing meters per second. Meters per second. That's a velocity, isn't it? Distance per time. Distance per time. That's the units for velocity, meters per second. But we're changing our velocity every second. So see how it's a change in velocity. Our velocity is changing every second. So meters per second squared is the same thing as a meters per second per second. Does that make sense? You sure? I don't see many heads nodding. So the unit for acceleration is this. But the unit for velocity, distance, is measured in meters. Time is measured in seconds. So the units are meters per second. That's a velocity. So that tells us right there, oh, that represents a velocity, but that velocity is changing every second. So that reminds me, when I'm dealing with acceleration, you got to have two of those. It's meters per second every second. We'll do an example to help solidify that a little. For this course, you can get away with 10. I've set up any homework problems or whatnot that there'll only be one answer close. Whether you use either of these, all the others will be far enough away. It won't matter which one you use. You'll know which one's right. Or in WebAssign, the tolerance level will accept both answers. It just makes our math easier so we can focus on concepts instead of math. So this equation, I'm going to rewrite it. A change in velocity. That's like final velocity minus initial velocity, right? The difference between the two ends is acceleration times time. So this is often, here we go, I don't want this one on this side, so I'm going to add it to both sides to be balanced. And you get the final velocity is the initial velocity plus acceleration times time. Generically, this is going to be another guide to our thinking. It'll be your friend. And let's look at it. You're going yay fast. You start out at a certain velocity. You could be at rest, and this could be 0. Or you're already going 55 miles an hour. That's where you start. Yeah?
How come the G turned into a
This is specific when the acceleration is due to gravity. But there's other accelerations out there. So this, I'm showing you this formula works for any acceleration. So these are the same thing with the acceleration replaced as the acceleration due to gravity if you're dealing with things falling, which we will be more. Good question. So you're starting out at a certain velocity, whatever it is. Newton's first law, and you're happy not changing, right? But then some net force is applied to you and causes you to accelerate. In this case, it's Earth pulling on us. But you could be in your car going 55 miles an hour and you accelerate. You push on the accelerator pedal, right? So now you're accelerating for a certain amount of time. And this term is the change, right? That tells you how much you're going to change your velocity. So you're going to add velocity to what you were already doing and end up going faster, maybe 85 miles an hour. What if you hit the brake? You're going 55 miles an hour and you hit the brake. What happens? Yeah, your final velocity is going to be less than 55, right? You're still accelerating. Let's say you're driving this way. Point. Acceleration's a vector. It has direction. You're driving this way and you slam on the brake. Point which way the net force is on you. Come on, you guys aren't playing. Point. I'm a patient man. I'm serious. Point. I don't know if you guys get it or not. I see a few of you. You know, you're like.
Are you talking about the acceleration or about the
Yeah. You're tooling along at 55 miles an hour. You hit the brake. So your intuition tells you you're going to slow down, right? So I want you to point in the direction of that net force. We did it before. Let me review real fast. Here it's a block. Okay. So you're moving that way. Some force is propelling you. Some force, friction and air drag. If they're balanced, you maintain 55 miles an hour, correct? Do you remember this? We would say you're in equilibrium. A state of motion is not changing. 55 miles an hour. You're happy. But now you're messing things up. You hit the brake. The net force on this car is now in which direction? Thank you. More of you are pointing. Yeah, the net force will be this way. Because these won't be equal anymore. This will have gotten bigger. Now you have air resistance, friction, and the brake. It causes more friction. So if this is bigger than that side and you add them together, can you see they don't cancel each other out? The net force is not 0. And we draw our pictures. You like those cartoons? Here's a force body diagram. If you have this arrow that's about this long representing the magnitude of your retarding force, and this one trying to propel you represents its magnitude. So this much is kind of canceled out by that. And you're left with a net force that long. So you can even represent and have a feel for the relative magnitude of this net force. So the way it's drawn, that's roughly accurate. I didn't use a ruler. Does that make sense? So yeah, when you're braking, you still accelerate, but you're accelerating that way. When you hit the gas pedal, which way is the net force? That way, because you just increased this for a while. And the acceleration will be that way. But they're both accelerations, and as long as you're accelerating for a certain amount of time, this will cause a change in velocity. And that change will change whatever the initial state was, whether you weren't moving or already moving. So this will be your friend to help you sum that up. Let's do this ball and do an example. All right. Force is acting on the ball right now. I'll make it simpler. Gravity, down. So the Earth's trying to accelerate it down. Its weight is the force. Force down. Okay? But it's not moving down, so something else is happening. The normal force, or the support force of my hand pushing up. You can tell they're balanced right now, right? I'm going to apply an upward force to it that'll be larger than its weight. And I'll get it to move up. Bummer. While it's in the air, what force is acting on it? Gravity. Wait, as soon as it leaves my hand, why does it keep going up though? Thrust. And what provided it?
Your hand.
Is it still providing it?
No.
Good. Once it leaves my hand, I'm no longer applying a force to it. That force got it to accelerate from 0 meters per second to something non-zero meters per second. That's its initial velocity, right, on its way up. But as it goes up, you can see what happens to it, right? It slows down. So its acceleration must be changing. It's decelerating. And what's causing that? You already said it. Gravity. Right, that's the acceleration. Okay, how about on its way back down? From the top down, what happens? Gravity's still acting. And what happens to the ball? It accelerates down. It picks up speed. Can you see at the top for a brief moment it stops? Right? There. There. So it's going fast. Slows down, stops, and then picks speed back up, and it's going fast again. Okay. You said acceleration's down when the ball's coming down. Which way is acceleration on the way up? From here to there. Here to there. Which way is the acceleration? What's causing the acceleration? Gravity. Which way is gravity acting? Down. Which way is the acceleration on the ball on its way up? Down. Gravity's always pulling down on it. Because things get a little like with this, because it can be moving one way, but the acceleration can be another, can't it? That's just like braking in the car. The car is moving this way, but you hit the brake, you're accelerating that way. See the confusion though? The car is still moving that way, but the force and the acceleration are that way. That's why it slows down. So if Earth is pulling on this back down as the ball is on its way up, that makes it slow down. You can see that. It does. It goes up, slows, stops, and keeps coming. So, oh yeah.
So the velocity changes though.
The velocity is always changing, isn't it?
Yes, because the direction is different. But the acceleration is the same.
Very good. Velocity is always changing. The direction changes. Acceleration's always the same. And you know the acceleration value now. What is it? 9.8 or 10 meters per second every second.
Okay, and one more question. Why is it, I got this one wrong in this homework, why is it not in equilibrium when it's staying
Oh, good, yeah, I wanted to cover the top now. So right at the top, right there, when it stops, what are the forces acting on it when it's at the very top?
Gravity.
Gravity's still acting, but it's not moving. It's changing direction,
And it goes down.
but it's slowed down, it's stopped, and so yeah, it's changing. Like you said, it's changing direction. So there's still a force applied. There's a net force, gravity. So it's still accelerating. There's a net force that's causing a change in motion. So even at the top, for that brief instant, that instantaneous velocity at the top is 0. It's not moving for an instant. But it still has a net force that's not 0. It's still being accelerated down by gravity. See, that can be weird too. Wait, it's not even moving. How can it be accelerating? Well, for that brief instant, it certainly can. Does that make sense? Yeah. Yeah, that's true. Good point. Equilibrium's equilibrium. I use it generically. Your book specifies between mechanical equilibrium and dynamic equilibrium. Roughly, mechanical equilibrium is when things aren't moving and they're balanced. Dynamic equilibrium is when they are moving, but they're still balanced. So like going 55 miles down the road and maintaining that speed, you're in dynamic equilibrium. Because there's forces, but there's no net force. But you're moving. You're in equilibrium still. Where that is not in dynamic equilibrium. We can say just mechanical equilibrium. Yeah, thank you, because that does get confusing. So yeah, there you go at the top. So we didn't even get to this one. That's all right. I can do it next time. Something I wanted to show you. Last thing, because that's all we got time for. Look at it in your book, or think it through. If g is 10, acceleration due to gravity is 10, and you start at rest, so you have a ball, it's not moving, and you drop it. After 1 second of falling, how fast is it going? So at 1 second, what's the new velocity? I've heard some people say it, giving others a chance to, you're making a prediction, right? There's two ways to look at this now. One, you can just plug and chug, put it in here. What's the initial velocity? 0. What's the acceleration? 10. How long did it fall? 1. Calculate it out, you got your answer. I hope, though, you'll think of it conceptually, because this takes no thought now. Look at it this way. You fell for, the rate of change of your velocity is 10 meters per second every second. So after 1 second, what's your velocity changed? 10 meters per second. The change was 10 meters per second every second. So if you start out at 0, after 1 second, the change is 10. How fast are you going after 2 seconds? 20. 3 seconds? 150 seconds. 150 times 10, 1,500 meters per second. That's how fast you're going, because that's the rate that your velocity changes. You can plug 150 in here, you'll get the same answer. But this way, hopefully it makes more sense to you. There's a chart in chapter 3 on that you can review. We'll start there next time. Thanks.